right? So in calorimetry, what we'll be learning is the relation between heat and temperature. Okay. Consider an object like this, some random solid I'm taking. Okay, fine. Now, if you want to raise its temperature, obviously you'll have to supply heat. There may be some other ways also, but supplying heat is a very common way of raising temperature. Now, if you supply heat to a solid, now you will observe its temperature rising. Okay, supply heat, so temperature rises. Okay, the amount of temperature rise, delta T, and the heat that you supply, let's call it delta Q. Okay, capital Q is the symbol we use to represent heat. Delta Q is like amount of heat supplied. Do you think these two are proportional or not? Like if you want more temperature change, will you need to supply more heat or not? Just quickly answer yes or no.
Yes.
Definitely. Okay. So delta T, the temperature change that you want to bring about in the object, will be proportional to delta Q. Fine. Now consider two objects made of the same material. One of this size, another one maybe much smaller. This we had discussed at the beginning of this chapter also when we discussed the relation between, not relation, the difference between heat and temperature. So let's say there are two different objects, I mean, two objects of different sizes made of the same material. Suppose you want to bring about a temperature change of delta T in both of them. Means you want to raise the temperature by the same amount. Which one requires more heat? The bigger one or the smaller one? Or do you think they will require the same amount of heat? To raise the temperatures of both stones by the same amount, which one requires more heat? Okay, I got one answer as the smaller one needs more heat, one answer as the bigger one needs more heat because it has more molecules. Okay, the correct answer is that the bigger one will require more heat. Okay, see, raising temperature means what? Temperature is a measure of energy per molecule. Now you want to raise the temperature by the same amount, means per molecule you want to supply the same amount of heat. But the bigger one has more number of molecules, so you'll need to supply more heat. Okay, simple. And what's the difference between the bigger one and the smaller one? The number of molecules. You can also say it's the mass. Fine. So for a given temperature change, the heat to be supplied is proportional to the mass of the object. More mass requires more amount of heat for the same temperature change. Okay, the bigger one will require more heat. Vanilla, why did you think the smaller one will need more heat? Any reasonable explanation you can give to that?
Sir, I thought the smaller one should expand as much as the bigger ones.
Okay, no, no, this is not about expansion. It's just about temperature change. Okay, fine, fine. Next, suppose there are two stones or two solid objects, but made of different materials. Fine. Let's say one is like this and another one, fine. I'm using pictures of asteroids, but that's fine. Assume they have the same mass. Okay, M and M. And you want, they are both initially at same temperature, and you want to bring about the same temperature change in both of them. Let's say they are both initially at 25 degrees Celsius, and you want to raise the temperature to 40 degrees C. Do you think they will require the same amount of heat, or maybe they will need different amounts of heat? You can't exactly tell which needs more heat, but do you think they will always need the same amount of heat, or could the heat required be different? We are not talking about expansion, we are talking about temperature change. To bring about the same change in temperature, do you think they will need the same amount of heat or different amounts of heat? Pawan, what do you think? Different. Okay. Sohan is also saying different. Can you justify your answer, any one of you? Unmute and tell. Why do you think they will need different amounts of heat?
But because the nature of the molecule in both of them are different.
Okay, that is correct only. But see, temperature is a measure of energy supplied per molecule. No. Now you want to bring about the same change in temperature. So per molecule, you have to give the same amount of energy. Nature of molecule, how does it matter?
Means its ability to absorb the energy we are supplying.
It will absorb, no? Where, what else can it do? Okay, okay, fine. Anyway, the answer you have given to some extent it is correct only. But see, their masses are same, doesn't mean they have the same number of molecules. Correct only, no? Densities could be different. Fine. Or one of them can have heavier molecules than the other. The one which has heavier molecules will have less number of molecules. The one which has lighter molecules will have more number of molecules for the same mass. Okay. Now, per molecule, the heat you need to supply is the same because you want the same change in temperature in both of them. So, per molecule, the energy to be supplied is the same, but the number of molecules can be different. Therefore, the amount of heat supplied, the amount of heat required to be supplied can be different. Okay. So, the heat required to bring about a certain temperature change depends on the material as well. Fine. So, we can connect all these. The temperature change that results due to a heat supply. Fine. There is an equation relating them. We can write delta Q is equal to, or okay, let's put all these together. Now, first we saw that delta Q is proportional to delta T. The heat you need to supply is proportional to the temperature change that you want to bring about. And then we saw that delta Q is proportional to M. More the mass, okay, more the heat you need to supply, provided material is same and temperature change is same. So delta Q is proportional to M. And it also depends on the material. So putting all these together, you get delta Q is equal to M delta T, and the proportionality constant is called S. Okay, so we write delta Q is equal to ms delta T. In some books, you may find it as Q is equal to ms delta T. Nothing wrong in that. Okay, but writing it this way has a slight advantage. You can write it in differential form also. dq, the small amount of heat supplied, is equal to ms dt. Okay, resulting in the small temperature change dt. Right. Now, you understood that delta Q is the heat that we supply, delta T is the temperature change, M is the mass of the object. S here is called as specific heat or specific heat capacity. Sometimes they just call it specific heat. It means the same thing. Okay. So we can write S is equal to delta Q divided by M delta T. So based on this formula, we can define specific heat of a material. Okay. S is obviously a factor which depends on the material. Let me mention it here. Okay. So how do you define specific heat? Listen, if mass is 1 unit and temperature change is 1 unit, then S becomes equal to delta Q. So we define specific heat like this. Specific heat is the heat required to change the temperature of, okay, heat required to change the temperature of unit mass of a material. Unit mass means M should be equal to 1. It could be in SI units or CGS units, unit mass. Okay. Or any other unit also, but the numerical value should be 1 to change the temperature of unit mass by 1 unit. The temperature change also should be 1 unit. For that, how much ever heat is necessary is what you call as specific heat. Fine. So based on this formula, quickly derive the SI unit and dimensional formula of specific heat, all of you. Okay, it is smallest. We use the symbol smallest to represent specific heat. Give me the SI unit and dimensional formula. Fine. SI unit of heat is joule, mass is kilogram, temperature change, as I said, you can write per Kelvin. Kelvin is the SI unit of temperature, but notice here that this is temperature change. Fine. And temperature changes are same on the Kelvin scale and also on the Celsius scale. So you can write the unit as joule per kg per Kelvin. Fine. You can also write it as joule per kg per Celsius degree. Okay. Effectively, they are the same. And dimensional formula, heat is ml square. Energy is ml square T power minus 2 divided by, there is mass here and delta T is temperature change in Kelvin. Mass gets cancelled. So, okay. The ones who gave dimensional formulas L square T power minus 3, you took T as time. No, T is temperature. So it will be, M will get cancelled. L square T power minus 2 K power minus 1. Okay, fine. So understand that specific heat is the heat needed to change the temperature of 1 unit mass of a material by 1 unit change in temperature. By 1 unit. Okay. Then, okay. Now, if you consider water, to raise the temperature of water, okay, or to raise the temperature of 1 gram of water, particularly from 14.5 degrees C to 15.5 degrees C. Okay, now 14.5 to 15.5 is 1 unit change only, no? Okay, and gram is also 1 unit only. In the CGS system, it is 1 unit. So to raise the temperature of 1 gram of water from 14.5 degrees to 15.5 degrees, the heat required is exactly 1 calorie. In fact, this is how a calorie was defined. Okay, calorie was one of the earliest used units of heat. Before the SI system came into existence, scientists used to use this unit for heat called calorie. Okay, so how is calorie defined? Calorie is the heat needed to raise the temperature of 1 gram of water, particularly from 14.5 to 15.5 degrees C. Now, 1 gram is 1 unit, 14.5 to 15.5 is 1 unit. So basically, calorie is the heat required to raise the temperature of unit mass of water by 1 unit. Then, by definition itself, calorie becomes the specific heat of water. Okay, I should not say calorie actually. I have to write the proper unit. Specific heat of water can be written as 1 calorie per gram per Celsius degree. Okay, so by definition itself, 1 calorie per gram per Celsius degree becomes the specific heat of water. That is how calorie was defined. Now, why particularly 14.5 to 15.5? Now see, 14.5 to 15.5 is 1 unit change in temperature. Some 44.5 to 45.5 will also be 1 unit change in temperature. But this 1 unit requires a different amount of heat compared to that 1 unit. So what I'm trying to tell you is, change of 1 unit in temperature may require different amounts of heat. Okay, so every 1 unit change in temperature won't need the same amount of heat. But in your syllabus, usually you will assume it is the same. Okay, so suppose specific heat of a material is given to you. Let's say specific heat of some material, okay, some solid is given to you as some 2000 joule per kg per Celsius degree. Then whether you are changing its temperature from 1 degree to 2 degree or 10 degree to 11 degree or 21 degrees to 22 degrees, any 1 unit change in temperature, you will assume the same heat is needed. But in reality, practically, it's not the same. Okay. That is why calorie was specifically defined for this change in temperature. For other changes in temperature, in reality, even if the change is 1 unit, the amount of heat needed will be slightly different. There may not be a drastic variation, but difference will be there. Fine. But as far as your syllabus is concerned, you will assume specific heat is uniform across all temperatures. Okay. But specific heat will change based on state of matter. As long as water remains as water, you can use specific heat as 1 calorie per gram per Celsius degree. But water can change into other states also. It can convert to ice, it can convert to steam. Okay. In ice form, the specific heat will be significantly different. In steam form, the specific heat will be significantly different. Okay. So to summarize, what I want to say is, unless otherwise specified in the question, you'll assume specific heat is fixed for a certain state, okay, of that material. Suppose steel in solid form, it will have one specific heat. Okay. Steel when converted to liquid will have one specific heat. Any temperature of liquid, it will have the same specific heat. Any temperature of solid, it will have the same specific heat. Okay. But in reality, the values will change slightly. So, but if it is not specified in the question, we'll assume it maintains a fixed specific heat. Okay. So we just discussed the formula that delta Q is equal to ms delta T. So based on the amount of heat supplied, how much temperature change can be produced, you can find out using this formula. But remember, this formula is applicable only when the state of matter does not change. Means conversion should not be happening. Solid converting to liquid or liquid converting to solid, liquid converting to vapor or vapor converting to liquid. Those changes should not be happening. So only when state does not change, state of matter does not change, you can use this formula. Okay, let's solve some simple problems based on this. First, let's say 2000 joules of heat is needed to raise the temperature of 4 kg of an object or 4 kg of some material from say 21 degrees C to 26 degrees C. Okay, calculate its specific heat. Now, we have to assume that during this temperature change, 21 to 26, the state of matter is not changing. So if it's solid, it remains as solid. If it's liquid, it remains as liquid. That assumption you have to make. Okay. Solve this quickly. Okay. This is a direct application of this formula. Okay. S is equal to delta Q by m delta T. The heat needed is 2000 joules for how much mass? 4 kg. And the temperature change 21 to 26 is 5 degrees. That's all. All the given terms are in fine. Temperature is not in SI units, but 21 to 26 degrees C is a change in temperature of 5 Celsius degrees, and it is same as 5 Kelvin. Okay. So substituting it here, 4 by 4, 400 by 4 becomes 100 joule per kg. Per Kelvin you can write, or per Celsius degree also you can write, because these are temperature changes. Only temperature will not be same on Celsius and Kelvin scale, but changes in temperature will be same. Keep that point in mind. Okay. Next question. Consider this label. Fine. So this is the power saving guide of a heater, water heater. Okay. Now observe what is given here. Standing loss, that's fine. That's the rate at which it loses heat. Let it be. Equipment, whatever, rated capacity 25 liters. What does this word rated capacity mean? Rated capacity, and below that you have rated power also. Okay. That basically rated means maximum. So maximum capacity that it can hold is 25 liters. And rated power, maximum power that it consumes is 2000 watts. Okay. Now it's not necessary that all the electrical power consumed gets uh, supplied as heat to the water inside. Some heat may be lost to the surroundings, some sound may be generated. So there will be some loss of energy as well. All the power consumed won't get converted to, uh, or all the energy consumed, all the electrical energy consumed won't get converted to heat supplied to water itself. Okay, assuming you are heating water. Okay, so this heater has 2000 watts. Let's assume an ideal case. Okay, let's say power. Power means what? Energy consumed per unit time. So assume this is an ideal heater. All the electrical energy is getting transferred as heat to the water inside. So I can say power supplied. Power consumed is equal to power supplied. Let us assume is 2000 watts. Okay, you know what is watts, you can convert it to different units also. At this rate, specific heat of water we know is 1 calorie per gram per Celsius degree. This is not in SI units. Now we had discussed the conversion from calories to joules a few classes earlier when we discussed basic units of heat. 1 calorie is 4.2 joules. Okay, so this is actually 4.2 joule per gram. Okay, per gram means per 10 power minus 3 kg. Per Celsius degree, you can write it as it is. So that basically becomes 4200 joule per kg per Celsius degree. This is the specific heat of water in SI units. And remember, water has one of the highest specific heats of all the natural materials that we find. Okay, there is a practical application also of this. So note down these values. The power supplied to water is 2000 watts, means heat is supplied at that rate. Specific heat of water 4200, let us approximate it to 4000 just for convenience in calculation. Joule per kg per Celsius degree. Okay. So you know the rate at which heat is supplied and you know how much heat is needed to raise the temperature of 1 kg of water by 1 Celsius degree. I want you to find out how much time it takes to heat. How much water shall we assume? Let's say some 50 liters of water. Can any of you quickly tell me the density of water? 50 liters will weigh how much? Because without that, you can't use specific heat formula. How much is the density of water? I told you this many times. Water density is very easy to remember. 1 kg of water weighs 1 liter. 1 liter of water weighs 1 kg. Okay. So 50 liters means 50 kgs. Fine. So find out how much time it takes using this heater to heat 50 liters of water from 20 degrees to 60 degrees. Fine. Heater provides heat to water at a rate of 2000 watts. That's the rate of transfer of heat. And specific heat of water, take it as 4000 joule per kg per Celsius degree. Find out how much time will be required. You can give your answer in seconds, or if you want to convert it to other units like minutes and hours also, you can convert. Solve this quickly. I'll give you 2 minutes. You have to find out how much time it takes to heat certain amount of water. Now, basically, we are talking about heat, and heat can be related to time only through this power. 2000 watts means what? 2000 joules per second. Okay, so in 1 second, the heater transfers 2000 joules to water. So if you know totally how much heat is needed, you can tell how many seconds will be required. Simple. Okay. Now what do we want to do? We want to raise the temperature of 50 kg of water from 20 to 60. So we'll find out the heat required first. Delta Q is equal to mass is 50. See, actually the volume was given in the problem, 50 liters. Based on density of water, that 1 liter weighs 1 kg, we were able to convert it to 50 kg. M. Specific heat of water, I asked you to take it as 4000 in SI units. And the temperature change, 20 to 60, the change is 40. That's all. 4, 4, 16, 16, 5 is 80. 80 into 10 power 5, or you can write 8 into 10 power 6 joules. That much heat will be needed. Okay. Now, power is heat supplied divided by time taken. So, time taken will be heat supplied divided by power. Heat supplied is this much, 8 into 10 power 6 joules. The power is 2000 watts, 2 into 10 power 3 joules per second. Joules will cancel. The answer will be in seconds. So that is 4 into 10 power 3, 4000 seconds. So slightly more than 1 hour, okay, will be needed. Fine. Next, as I was saying, water has one of the highest specific heats of all naturally available materials. Now, what is specific heat? Delta Q divided by m delta T, the heat required to raise the temperature of a material of unit mass of material by 1 unit. Okay. Now, specific heat is high means it is difficult to raise the temperature of that material compared to other materials of the same mass. That is what high specific heat means. You will need to supply more heat to raise its temperature. Now, how can we make use of that property? Now, if any of you have experienced this, you might have heard people saying, like, if you have fever or if a baby child has fever, they ask they ask that more water be given to the child. Okay. How does drinking water help in controlling fever? What is fever? Basically, high body temperature. Now, suppose water is at room temperature. Now, definitely the person having fever, that person will be at higher temperature compared to room temperature. Okay, you can feel like when you touch the person who has fever, you can feel that they are at higher temperature compared to when you touch another object in the room. So, room temperature is lower, person temperature is higher. So, water is at room temperature. Suppose there is a glass of water at room temperature. If the person drinks water, generally what will happen? Heat gets transferred. We discussed this at the beginning of this chapter itself. Heat is a form of energy which gets transferred from an object of high temperature to an object of low temperature. So, if a person with fever drinks water, person's body is at higher temperature, water is at lower temperature, heat transfer will occur from the person's body to water. Till when will heat transfer occur? Heat will keep on getting transferred as long as there is a temperature difference. As long as person's body is at higher temperature and water is at lower temperature, body will keep losing heat to water. So body temperature will reduce. Okay, depends on the amount of water you drink also, but body temperature will reduce. Water will absorb heat from the person's body. And how is the high specific heat of water helpful here? Okay, basically, even if what because the specific heat is high, even if water absorbs a lot of heat, the temperature change of water will be low. Okay. So water has a capacity to absorb more heat before its temperature rises significantly. Now, person's body is at higher temperature. Water that the person is drinking is at lower temperature. So from the body of the person, heat will be transferred to water, and more amount of heat transfer can happen before their temperatures match. Okay. So that is how drinking water during fever helps. There are some other like applications also in many vehicles and even in industrial machinery. Water is used as a coolant. Basically, as the name suggests, coolant is a substance which is used to keep the temperature of a machine under control. Okay, to cool down the machine. Cooling down the machine means what? Taking away heat from it. Now, when will anything be able to take heat from something else? When will A be able to take heat from B? When A is at lower temperature than B. Then only A can take heat from B. Now, by passing water through the machine, what effectively is achieved is heat from the machine gets transferred to water. And when will heat get transferred from machine to water? When water is at lower temperature, no? Water's temperature should not become equal to that of the machine or greater than that of the machine. Okay. And water has this capacity to absorb a lot of heat before raising its temperature significantly. Fine. That is why water is used as a coolant. And in general, okay, there are some other synthetic coolants also. Okay. So in general, coolant should have high specific heat such that it will be able to absorb a lot of heat without a significant change in its temperature. Okay, almost every vehicle uses a coolant. Okay, some are water cooled, some use synthetic coolants, but this is the purpose of a coolant, and this is the property that a coolant must have: high specific heat. Okay, fine. So tomorrow's class we will discuss more about this calorimetry heat temperature relations. We'll also discuss change of state. Okay, melting, boiling, freezing, okay, condensation, all these processes. Okay, thank you all. We'll continue tomorrow.
Thank you.